Hello and welcome to the LedaFlow version 2.6 release webinar, and thank you for accepting the invitation. My name is Mike Branchflower. I'm the Strategic Sales Manager for production inside Kongsberg Digital. If you're having any issues with audio, please go to the audio pane and click on Sound Check in blue, and that will guide you through the process. You can also join over the phone as well. There are instructions inside the chat window as well, which can help you. You'll all have the opportunity to submit questions, so please type them into the questions pane and send them in as we go along, as we do the presentation and demonstration. And what we will do is answer as many as we can at the end, and the ones we can't answer, we'll get back to you afterwards. I'm now going to hand over to Wouter Dijkhuizen. He's the LedaFlow product champion, and he will present and demonstrate the new features in version 2.6 of LedaFlow.
Yeah, thank you, Mike.
Okay.
Is it showing my screen?
Yeah, all good, Wouter.
Okay, thank you. Thanks for the introduction, Mike. So as said, this is the webinar for the LedaFlow 2.6 release, which was released just a few weeks ago before Easter. So we'll go through some of the major improvements in LedaFlow 2.6, that being the multi-phase flow model improvements, something about sand transportation, some of the model improvements in the single component model, which amongst other things is used for CO2 transport, a little bit about the different mass transfer terms in LedaFlow, which have been adjusted, and finally some other model improvements. And then all the way at the end, I will give a short demonstration about the sand transport feature. I should note here that there's also more improvements and bug fixes in this release, more than what I can present here. And you can find more details about that in the release notes. So first of all, the multi-phase flow model improvements have been changed, which is a tradition. We do that every major release. So the focus area this time was on water accumulation at low flow rates for oil water and gas oil water flows. So to do this, we've conducted some so-called screening experiments in the Tiller large-scale flow loop in Trondheim. So the idea here is that these experiments are specially designed to find the discontinuous transition from high to low holdup. Let's see if I can get a pointer here. Yeah, so the idea is that you can get, if you decrease the superficial velocity of oil, at some point, if the velocity becomes low enough, then you get this discontinuous increase in the water holdup. So it jumps from a low to a high value. And it's possible to replicate that in these special experiments, because it's possible by adjusting the conditions to have this both the low and the high holdup solution. Yep. Am I back? Yep. Yeah, it's possible to get both the low and the high holdup solution in this single experiment. So you can get this jump in the middle of the pipeline, and then the low holdup and the high holdup can be measured. And the pair of the two, it will give you the holdup, and based on the flow rates, you can extract this critical flow rate where this jump occurs. So that's quite a good way of doing these experiments. And the sole purpose of these experiments is to improve the oil-water interface friction. So this has a very good properties to make this adjustment in the model. So then looking at the performance, so this is the performance shown for 8-inch oil-water experiments. So what you can see here in the dotted line in blue, that is the performance of LedaFlow 2.5. And then the red line is the performance of LedaFlow 2.6. And then the black dots over here with small arrow bars, those are the experiments. You can see that there's a good improvement going to LedaFlow 2.6. We're capturing nicely where the discontinuous transition is in the water holdup. And overall, we just predict the water holdup a little bit better than in the LedaFlow 2.5. So the 12-inch experimental data that was also conducted in the tiller loop that shows a similar improvement. So we don't really need to look at that here. And also we have some other data sets that we've used to evaluate if this was working correctly. They also show a clear improvement for all of them. So that is at smaller pipe diameters. And I can also note that there's a little effect on the pressure drop. So the main improvement here is on the water hold. Then on to the new feature in LedaFlow. So from before, we already had a sand indicator, as we call it, in LedaFlow, which allows you to predict where sand might accumulate. So it's kind of like a risk-based approach, much like the hydrate margins, for instance. So this was based on the Oroskar Turian and Danielson sand models, which both give you a critical water velocity that is required to keep the sand moving. And then below this critical velocity, you can expect the sand to start accumulating in the pipe. So what we've done now is to take this one step further with the sand transport feature, which actually tracks the sand particles throughout the pipe network. And then it will show you not only where the sand might accumulate, but it will also show you how much sand will accumulate. In order to do this, we are modeling 6 different sizes of sand as custom fluids, which allows us to track them through the pipe network. We're assuming no slip between the water phase and the particles. And the sand deposition entrainment is based on the difference between the critical and actual water velocities. That is the formula shown at the bottom of the screen. So the deposition entrainment process is reversible. So if the velocity drops below the critical velocity, then you get deposition in the pipe. And as soon as the water velocity is high enough again, then the sand will be entrained again. So it's possible for the sand bed to, for instance, slowly creep along the pipe like that. And then the effect of the sand deposit is that it reduces the surface area and volume in the pipe, which will result in higher velocities and pressure drop. So I'll demonstrate that in the demonstration at the end of this session. Then some of the improvements for the single components. So the single component model in LedaFlow, this is a generic model for any single component, but we've especially been using it for CO2 transport because we're involved in the R&D project, which is also where these improvements come from. So we've been focusing on improving the robustness of the model and also the calculation speed. So first of all, we've fixed a problem with that condensation of gas was not working properly in the bubbly flow regime. So for CO2, it's quite rare to have the bubbly flow regime in the first place, but still it's good to make it consistent. So the surface area for the phase change was 0 in the previous version of LedaFlow. And we've now added a reasonable surface area for between the bubbles and the liquid phase, which does give condensation now. So this improves mainly the stability, since the phase change is no longer delayed until the flow regime changes. So previously, it was possible for the simulation to continue until the regime changed, and then you would get a very sudden phase change, which is not so good for the numerical stability particularly. Also, we've implemented a phase change term now for supercritical conditions. So that is shown in the plot on the bottom right. So this, with the arrow, it's indicated where the critical point for CO2 is. And then we're extrapolating this, the phase curve for the single component. And we're now also applying phase change when we're in supercritical conditions, so that we get transition from gas-like dense phase to a liquid-like dense phase. So this makes the volume fractions in the simulation consistent with the phase diagram. that's in supercritical conditions, the gas and liquid properties are the same anyway, so it's not, it doesn't really have any major consequences for the simulation. But again, this improves the numerical stability, because when we later on in the simulation we could move back to subcritical conditions, for instance by doing a depressurization, and it will be much more stable now, because there's no unphysical phase change when dropping below the subcritical conditions, because the labeling of the phases is already consistent. So on one side is gas, the other side is consistently liquid, so we don't get into any numerical issues there. And then finally, the calculation speed of the PVT calculations has been greatly improved. It was quite expensive before, but we've managed to achieve an order of magnitude speed improvement with no loss of accuracy by just optimizing the calculations. So this doesn't really change the results in any significant way, but it's much faster, which is good. Then on to the different mass transfer terms in LedaFlow. So for PVT table cases and cases with black oil PVT, we're using the so-called PVT mass transfer term. So here we have an option called oil evaporation, which is changing the, you can turn this on and off. It's operating on the transient term of this. So basically that is the mass transfer term in the cell, not the convective terms that operate between different cells. So this term is now enabled by default. So we're not changing the model, we're just changing the default setting if you're creating a new case in LedaFlow 2.6. And this is important because if there's large dynamics in your case, like for instance in depressurization, this will change the results quite a bit. So it will improve the results by having more gas evaporate from the oil phase. That's why we're mentioning it here. There's also a new type of custom fluid, which is called the PVT type. So this new custom fluid is based on PVT tables, and it also uses PVT mass transfer. So for instance, it's possible to have some gas evaporate from the oil phase. The intended use of this new custom fluid is for dead oil circulation, for instance, which is a type of displacement operation. And what is special for these kind of cases, if you do this in deep water risers, then it might be necessary to have some gas evaporate from the oil at some point in order to prevent vacuum conditions. And just because of that, we had to create a new custom fluid type which can use this PVT mass transfer. I should also note that this is not intended for mixing production streams with different GORs, because the mixing rule that we use for the PVT table gas fraction is not designed for that. So the results will not be that accurate. So we recommend to only use this for displacement type simulations. And then finally, the composition tracking. It uses a different kind of mass transfer term. There we've focused on the evaporation from oil at low gas volume fractions. So we've implemented an option there that we call automatic mass transfer tuning, because we were having some issues with the gas starting to form in the oil phase, especially in vertical pipes. And the reason for that problem was that we didn't have enough surface area to begin with. So if you imagine a pipe filled with oil, and at some point we drop below the bubble pressure, then gas should appear. But this was taking too long previously in LedaFlow. And that's why we're applying this automatic mass transfer tuning now. And it gives a better prediction of when the gas starts to appear by increasing the surface area. I should note here that this tuning is inversely proportional with the gas volume fraction. So if there's enough surface area, this is not doing anything basically. Some other model improvements in LedaFlow 2.6. So we've implemented some new corrosion models. Some from before we already had the NORSOC model available, but we're now also supporting the VART and IFE top-of-line corrosion model. Now I can add here that it is possible to activate all these corrosion models by default. Or we can activate them all at the same time, so it's possible to compare the results for all of them. it's not necessary to choose one or the other. And then finally, for hydrate transport, we now have some new advanced options there. So we have the hold time option, which allows you to control the delay before hydrate formation based on specialized lab data. That is the plot shown on the bottom right of the screen. So if you have this data for the hold time as a function of the subcooling, it's possible to enter this in the form of a table. And then LedaFlow will delay the formation of hydrates in the pipe using this experimental data. As you can see, it's there's quite a significant effect of different degrees of subcooling. So yeah, this is quite important for certain advanced users. Also, it's possible to use the water surface area now as well for hydrate formation. Previously, only the hydrate particle surface area was used as the active surface area for formation of hydrates. But if you want, you can also use the water surface area now. Okay, then we go to the demonstration of the sand transport feature. So what I would like to demonstrate is just how to set up this sand transport feature. So basically, it's an option that can be enabled for any kind of simulation. So what I've done here for demonstration purposes is to have a very simple pipeline profile. Just to make it interesting, I've taken a 1 kilometer pipeline and I've applied a sinusoidal shape to it, so we can have a look at what happens when we start going up and downhill. This will be interesting because we know that in the uphill sections there will be issues carrying the water phase uphill, and that will make it interesting for the sand deposition. So that's why I've applied this specific shape to the pipeline. So just to look at the different options. So the sand transport, it can be enabled in the case settings here. It's just a matter of turning it on. And then the settings are quite simple. You have to choose the transport model here, as opposed to the indicator, which was the previous implementation for sand transport. So you can choose whether or not you want to do the risk-based approach, or you want to do the transport option. And then there's only really two main settings in this window. The packing density, which means in this case that there will be 60% sand and the other 40% will be made up of water, because there will be some water in between the grains of sand. And then the development length scale, which is basically a tuning factor for the mass transfer term in the sand transport. Okay, and when you turn on the sand deposition, also this custom fluid tracking option will be enabled by default. And then what you get is 6 different particle sizes of sand, which are all defined as custom fluids. And if you want, you can change the density here, but this has already been pre-configured for sand, basically. So it's unlikely that you have to change this density a lot. Okay, that is the model configuration, basically. Besides that, there's not really any change in PVT or anything else that we need to worry about. The only other thing that is important is that you need to add the sand at all the inlets to the pipe model. So this flow boundary, for instance, you can see that I've configured a small amount of sand for every particle size, basically. So what you're giving here is the total mass fraction of sand, and these are flowing mass fractions. And then in order to demonstrate this feature over here, what I've done with this case is to reduce the flow rate at the inlet from 60 to 50 kilograms per second, and that will cause some sand to fall out, so we can have a look at the results for that. This sand deposition process, it's typically quite slow. So I've already pre-run this case for 1 million seconds so that we reach steady state. Then it's possible to look at results. So we have a plot template for this, which is called sand deposition model. And if we plot this result, we can have a look at dynamic results. So at the start of the simulation, we can see that the water velocity in the pipeline, it's above the critical velocity predicted by the sand model. So the water velocity is sufficient to keep all the sand mobile. Then if we just play this animation, need to speed it up a little bit. So we're running at 1,000 times real time now. Now we can see that when the flow rate is changed at the inlet, in part of the pipeline, the water velocity drops below the critical velocity, which means that sand will start to accumulate, which is what you can see at the bottom here. So the bigger particle sizes of sand, they will start to accumulate in the pipeline. Now we can speed it up a bit more, maybe 10,000 times in real time. So you can see the sand is now accumulating in this uphill section of the pipeline. So it's only the two biggest particle sizes that are accumulating now. And while the sand is accumulating, you can see that the water velocity is increasing. So this is happening because the sand is blocking the flow, which is causing the water velocity to increase again. So, and because the water velocity increases, this will basically turn into some equilibrium situation, where the velocity of the water phase, it will match exactly the critical velocity at steady state. So essentially, we've constricted the flow in the pipe to a certain degree, and that will determine how much sand can accumulate at equilibrium. So in the end, you can see that only the biggest sand particle size, it will remain in the pipe, and then the velocities will be approximately equal between the critical velocity and the water velocity. We can just go to the end of the simulation. Here we can see that now we've accumulated approximately 7% by volume of sand in the bottom of the pipe, which is essentially this uphill section here of the pipeline. Yeah, so that is just a small demonstration of the sand deposition model. I think we'll keep it at that and now go to the questions.
Yeah, thank you, Wouter. Very good presentation and demonstration as always. We do have a number of questions, so let's go through those now, and I'll type in some answers as we go along. So let's have a look. The oil water friction improvement, is that improving water hold-up estimates for low flow rate cases or high flow rate or all cases?
This is especially important for low flow rate cases. So there's very little difference at normal production rates, but at low flow rates, this is particularly important.
Okay, very good. So it's mainly around low flow rates. That's good, thank you. Can we plot the sand critical velocity?
Yes, that was in this plot that I showed here.
Okay, the question may well have been asked just before you demoed it, I guess. So
yep.
Yeah, that's the answer is basically yes to plotting the critical velocity. Okay. Then we have a question around pure CO2 and impurities, about whether we can handle impurities in CO2. Do you want to elaborate on what we're doing there, please?
Yeah, at the moment we don't handle impurities and CO2 yet, but that is something that is under development. So we'll expand the model to handle CO2 with impurities in the future.
Yeah, so we're working in a JIP that's intending to address that issue. Okay, that's that one. We're probably on the last. Scroll down. There's a few more questions. This is an interesting question. Does the sand model work in transient conditions? Which flow regimes? Like, does it work with slug flow, for example? Any issues?
Yeah, it doesn't really matter what flow regime you have, because it's just based on the water velocity, basically.
Yeah, so it doesn't.
It basically works for any flow regime. And I would imagine that in slug flow, probably the velocities might be high enough to keep the sand moving.
Yeah. Okay, let's send that one. I don't know quite what you see at the other end. You might just see the answer and not the question, which may not make much sense. Okay, in the sand deposition model, it seems like the smaller particle sizes are dependent on the larger ones deposited. You show a mix of different particle sizes rather than a parametric study between sizes.
Yeah, so basically I have all these different particle sizes at the same time in the simulation.
Yeah, that's just because that's what you decided to do, isn't it? You don't have to have all of those different particle sizes, do you? You can choose.
The reason for that is that in reality, the sand that you have in your pipeline, it will probably be a distribution of different particle sizes. It's kind of rare to have only one different particle size.
Okay, so will we always have those sizes in every simulation, will we? And you have to define how much of each?
Yeah, you need to, as a user, you need to give how much of each particle size you have in the simulation. So in reality, you will have some kind of probably Gaussian shape distribution of that, which really depends on, typically it depends on what kind of formation you have in your wells.
Yeah, okay. But do you have to have each individual size, or could you say I've only got 3 of those sizes that we've defined, for
No,
example?
you can select whatever you want. So if you want one particle size, you can just use that one. You're totally free to do whatever you want.
Okay, so hopefully that's answered that question. But if you find we haven't quite answered the question as you'd like, just send us an email and we'll get back to you. Some good feedback on the sand demonstration and some questions around how does wax work? Does it work in the same way? I know it's a bit different than that, but can you draw any similarities or explain maybe how wax deposition is working?
Yeah, it's very different because wax deposition it's a thermodynamic process. So it's basically coming from the oil phase, and it's based on heat transfer. So it is actually very different from sand deposition.
Okay. What about the effect? I guess the effect of pressure drop increases.
Yeah, that's the only similarity, basically, that it kind of blocks the flow, but otherwise it behaves very differently from the sand transport.
I'm just typing in as we go along. I think this is the last question, which is good because we're nearly out of time. When the fluid velocity comes back to be higher than the critical velocity, what is the behavior of the sand bed already deposited? So
if the velocity increases, then you'll re-entrain all the sand again.
Or we re-entrain the sand that, yeah, we will re-entrain the sand that is, yeah, that will be transport, yeah. Yeah. Is that an instantaneous thing, or is it taking time to go, you know, back to how do you?
Yeah, as you can see in this simulation, just depositing the sand, it takes time, and the re-entrainment, it also takes time, because we have this kinetic mass transfer term for the sand. So it's not instantaneous, but it's relatively fast compared to the time it takes to transport the sand through the pipeline.
Very good. Okay, any more questions anybody wants to type in? I think I've answered them all. Oh no, hang on, sorry, I've scrolled back up. It must be. Okay, there's another another question about the impure CO2. Sorry, I missed that one earlier. So we have the answer for that one, and we're actually developing that kind of right now. So we don't have impurities being handled correctly at the moment. You can try and use it, but we can't guarantee the results. Can we see the effect on pressure drop in line with the increasing sand volume fraction? Absolutely, we can. So yes, that's what you were showing there at one point later. So that's okay, isn't it?
Yeah.
Yeah. So I'm just checking if there's any more questions. Seem to appear in different orders. Okay. For water accumulation, how is the viscosity of the water accounted for? For example, water plus meg.
Yeah, this is not really a part of these models, I think. So I'm not sure it affects either the Oscar and Turian or the Danielson model. But I would have to check the exact details of how they predict this critical velocity.
Okay, so I'll say that we'll check. We don't believe it's part of them. Yeah. That's not a parameter. Okay. The sand deposition model depends mainly on the water flow rates. Does it also work with other liquid hydrocarbons? Any modifications planned?
We don't really plan to modify this. Because yeah, in most situations the sand would be wetted by the water, and it mostly prefers to travel with the water phase, not so much with the oil.
So no development planned at the moment unless we find out we need to do that. Okay. Okay, I think we're going to have to. I'm actually coming up with a few more questions. What time are we on? I guess we're 1 minute over already. Okay, this is an interesting one. Is there any maximum limit on the particle size of sand?
Yeah, so these particle sizes that we've implemented, they're hard coded, so it's not possible to change them at the moment. But
Okay.
they should cover the most important particle sizes that you have in reality. And also, as you can see, the difference on the critical velocity is not enormous between these different particle sizes.
Yeah, yeah. Okay, let's just see if there's another couple of questions. Do the PVT mass transfer improvements change the results?
Yes, especially for dynamic cases like depressurizations.
Okay. Okay. I appreciate we're running over. It'd be good to just answer a couple more. So I appreciate if you have to go, then fair enough. But we're nearly done with the questions actually. I keep saying that, and people keep typing more in. So it's good that there's lots of questions. Let's have a look. Can we see the effect on pressure drop in line with the increasing sand volume fraction?
Yes, I can even try to plot that.
Okay, I'll type that in.
So let's plot the total pressure drop, and yeah, so you can, so it's very subtle in this case. So this first spike, you should disregard that. That is just a change in flow rate. But then if you look at this part of the pressure drop, so here you can see the effect of the sand accumulation on the pressure drop in this case. So the flow rates are not that high, so it's a rather small increase, but it is showing basically.
Okay, I think we're going to have to make this the last one because we are overrunning. Can we initialize with a certain amount of sand in the pipeline?
Yeah, in initialization in LedaFlow, what we're doing is putting the sand in the water phase throughout the pipe, but we're not initializing the sand bed at the bottom of the pipe. So you will need to run the dynamic simulation to get the sand accumulation.
Yeah. Yeah. Okay, I'm going to have to stop there. I know we haven't answered all the questions, but please contact us. I'm going to have a copy of them, so I'll get back to you individually. Yeah, okay, so I think we're going to have to stop there. So thanks, Wouter, and thanks to everyone for attending. You'll get a follow-up email. It should be within 1 day, so you can actually watch the video again if you'd like to do that. And as I've already said, if you get any questions in your mind after seeing this, then please just send me an email and we'll get back to you. On behalf of Kongsberg, thanks for joining the webinar, and we hope to see you at the next one. I should say stay safe and enjoy the rest of your day. Goodbye.